Have you ever stopped to contemplate the nature of time? We experience it as a constant flow, always moving forward, shaping our lives. But what exactly is time? And how is it intertwined with the very fabric of the universe? These are questions that have puzzled philosophers and scientists for centuries. Time is a fundamental aspect of our existence, yet it remains one of the most elusive and mysterious concepts in science. It governs our every moment, from the smallest subatomic interactions to the grand evolution of the cosmos. Understanding the nature of time is crucial to unraveling the deepest secrets of the universe. Is time merely a human construct, a way for our minds to make sense of the world, or is it a fundamental property of the universe? Ancient philosophers debated the nature of time, with some, like Aristotle, believing that time was infinite and unchanging, while others, like Heraclitus, argued that time was in constant flux. Today, physicists continue to grapple with the question of time's true nature. Some theories suggest that time is an illusion, a product of our perception rather than a fundamental aspect of reality. Others propose that time is real, but may behave differently than our everyday experience suggests. In the early 20th century, Albert Einstein revolutionized our understanding of time with his theory of relativity. Einstein proposed that time is not absolute, but is relative to the observer's motion and gravitational field. He also showed that time and space are inextricably linked, forming a four-dimensional fabric called space-time. Imagine a stretched sheet of rubber representing space-time. A massive object, like a star, placed on the sheet would cause a dip or curvature in the fabric. This curvature is what we experience as gravity. Einstein's theory showed that time is affected by gravity, slowing down in stronger gravitational fields. Einstein's theory of relativity has had a profound impact on our understanding of time and the universe. One of its most intriguing predictions is time dilation, which states that time slows down for objects moving at high speeds or in strong gravitational fields. Time dilation has been experimentally verified using atomic clocks flown on high-speed jets and satellites. The clocks on the moving objects run slightly slower than clocks on Earth, confirming Einstein's predictions. This effect has important implications for GPS technology, which relies on precise timekeeping. Section 5. Cosmic time travelers, black holes. Perhaps the most extreme example of time dilation occurs near black holes, incredibly dense objects with gravitational pull so strong that nothing, not even light, can escape. These cosmic phenomena are not just fascinating, they challenge our understanding of physics and the nature of the universe itself. The immense gravitational forces at play warp space-time in such a way that the usual rules of time and space cease to apply. As an object approaches a black hole, time slows down dramatically from the perspective of an outside observer. This effect, known as gravitational time dilation, means that clocks closer to the black hole tick more slowly compared to those further away. The closer you get to the event horizon, the more pronounced this effect becomes until time seems to almost stand still. If an astronaut were to fall into a black hole, time would appear to stop completely from their perspective at the event horizon, the point of no return. This boundary marks the limits beyond which nothing can escape the black hole's grasp. The astronaut would experience a bizarre and extreme form of time dilation, where moments stretch into infinity. However, from the perspective of an observer watching from a safe distance, the astronaut would appear to be frozen in time, their image redshifted and fading as they approach the event horizon. This redshift occurs because the light escaping from the astronaut is stretched to longer wavelengths by the intense gravitational field, making them appear increasingly red and dim. The observer would never actually see the astronaut cross the event horizon. Instead, they would seem to hover at the edge, forever on the brink of disappearing. Section 6. The Big Bang, time's beginning? Our current understanding of the universe suggests that it originated from an incredibly hot, dense state about 13.8 billion years ago in an event known as the Big Bang. But what happened before the Big Bang? Did time exist before the universe began? The Big Bang represents the limit of our current understanding of time. According to the theory of general relativity, time itself began at the Big Bang. However, some physicists believe that the Big Bang may not have been the absolute beginning, but rather a transition from a previous state of the universe. Section 7. Time's arrow, order from chaos. One of the most puzzling aspects of time is its asymmetry. Unlike space, which we can move through in any direction, time seems to have a preferred direction. This asymmetry is something we experience every day, yet it remains one of the most profound mysteries of the universe. We experience time as flowing in one direction, from the past to the future. This unidirectional flow is something we take for granted, but it raises important questions about the nature of reality. Why can't we remember the future, and why do we have memories of the past? This directionality of time is often referred to as the arrow of time. The concept of the arrow of time helps us understand why certain processes are irreversible. For example, we can mix cream into coffee, but we can't unmix it. But what determines the direction of time's arrow? Scientists and philosophers have pondered this question for centuries. The answer lies in the laws of physics, particularly the second law of thermodynamics. The arrow of time is closely related to the concept of entropy, a measure of disorder or randomness in a system. When we see a broken egg or shattered glass, we are witnessing an increase in entropy. The second law of thermodynamics states that entropy always increases over time in a closed system. This law is one of the fundamental principles of physics, and it explains why certain processes are irreversible. This means that the universe is constantly moving from a state of order to disorder, from low entropy to high entropy. This increase in entropy is what gives time its direction and makes the past different from the future. And this flow of entropy may be what gives time its direction. As we observe the world around us, we see countless examples of this principle in action. From the decay of organic matter to the erosion of landscapes, the arrow of time is always pointing forward, guiding the universe from order to chaos. Section 8. The quantum realm, time gets fuzzy. At the subatomic level, the world of quantum mechanics, time behaves even stranger than in the realm of relativity. Quantum mechanics suggests that at the smallest scales, time may not be continuous but rather quantized, meaning it exists in discrete units or packets. Moreover, in the quantum realm, the act of observation can influence the state of a system, including its temporal evolution. This raises profound questions about the nature of time and the role of the observer in shaping reality. Section 9. Time's enigmatic embrace. Time, the enigmatic and ever-present aspect of our existence, continues to captivate and mystify. It is a force that governs the rhythm of our lives, from the ticking of a clock to the vast cycles of the cosmos. We measure it, we feel it, and yet its true nature remains elusive. From the grand cosmic scales of black holes and the Big Bang, where time and space are intertwined in a cosmic dance, to the very birth of the universe itself, time has always been a central player in the story of existence. In the subatomic realm of quantum mechanics, time behaves in ways that defy our everyday experiences. Particles can exist in multiple states at once, and the flow of time can seem almost irrelevant. Time reveals its intricate dance with space, gravity, and the very fabric of reality. The theory of relativity shows us that time can stretch and contract, influenced by the presence of massive objects and the speed at which we move. As we delve deeper into the mysteries of the universe, our understanding of time continues to evolve. Scientists and philosophers alike ponder its true essence, seeking to unravel the secrets that lie within its flow. Our understanding of time will undoubtedly continue to evolve. With each new discovery, we peel back another layer of the cosmic onion, revealing more about the nature of time and its role in the universe. Perhaps one day we will unlock the secrets of time travel, a concept that has fascinated humanity for generations. The idea of moving through time, experiencing the past or the future firsthand, remains a tantalizing possibility. Or perhaps we will discover that time, as we currently perceive it, is but a small facet of a much grander and more complex cosmic tapestry. Our current understanding may be just the tip of the iceberg. The vast galaxy with its stars and cosmic tapestry reminds us of the infinite possibilities that lie beyond our current comprehension. Time may hold secrets that we have yet to even imagine. Until then, time will remain one of the most profound and enduring enigmas of the cosmos. It is a mystery that beckons us to explore, to question, and to dream. The journey to understand time is as infinite as time itself.